Okay, we want to talk about the graph of a rational function of the form r of x equals linear over quadratic. Now this is not linear over linear times linear. It's linear over quadratic because when I use lin or quad, I assume the quadratic expression is irreducible. Now when you see this, you aren't sure whether the denominator is going to be reducible or not. You got to set it equal to 0 and find out. Either that or factor it, in which case it's not reducible. Then it would be a linear over a linear times a linear if this thing would factor over the real numbers. Okay, so the first thing we do when we see a quadratic, rational function is we find the zeros of the numerator, zeros of the denominator. Zeros of the numerator are going to be zeros of the entire function unless they're matched by zeros of the denominator. Zeros of the denominator are points at which, when you get points with the property, when you get close to them, the denominator gets very tiny, because as the denominator gets close to 0, it's got to get tiny. And then you're going to have a tiny into something that ain't tiny, okay? And it's going to be big. Maybe big positive, maybe big negative, it's going to be big. Okay, well, that just to remind you of the context. Okay, so we start by finding the zeros of the numerator. There's a 0 at x equals -9. Might as well come out here and indicate -9 is the location of a 0. Zeros is the denominator. The discriminant of this denominator is -24. No real zeros, hence no vertical asymptotes. Meaning we don't have to do any of those vertical dotted lines that are going to indicate vertical asymptotes. Okay, what about the signs? Well, numerator is positive for x greater than -9. Any number bigger than -9 added to 9, like -8 added to 9, gives you a positive number. Also negative for x less than -9. Take a number less than -9, just even like -10. -10 and 9 is -1, that's negative, so the thing is negative everywhere to the left of -9. So the numerator is positive from here over, negative from here over. The denominator has no zeros. So it doesn't change sign. Okay? The denominator is +10 when x equals 0. so since it is zero, positive someplace, and never changes sign, it's always zero. So the numerator is positive from here on, negative from here to this side. The denominator is always positive, so on this interval here, let's just say, just going to take this from here to here, you have positive over positive, which is positive. So the graph is going to be above the x-axis everywhere, from here and to the right. And from here and to the left, you have positive over divided by negative. And let me write that as positive divided by negative this way, so we don't confuse the fraction bar with a negative sign. Use a slash. Okay? Positive slash negative, positive gives you positive, and a positive slash negative is negative. Again, because numerator and denominator are both positive here. Numerator, like I said, a numerator negative, denominator positive here makes the whole thing negative. So the whole graph is below the axis to the left of -9, above the axis to the right of -9. The y-intercept is, well, when x is 0, you get 9 over 10. If you really like decimals, we can say that's 0.9. So let's just say that's here. Okay, so it's got to be negative over here, positive over here. Now, we could maybe draw a graph that comes up from down here and up here and down here and then levels off, but that's not what happens. If that would satisfy all the conditions we have so far, my intercept would be here, be negative over here, be positive over here. It could come down from here and up through here and down here and wiggle around and go on up, as long as it doesn't make a loop and it stays above the x-axis. It satisfies all the conditions we've specified. However, if we look at what happens when x gets large, either large positive or large negative, we see that if x is big enough, the 9 isn't going to make much difference. The 4x plus 10 isn't going to make much difference. It's going to be like almost as though we have x over x squared. So, say for large x plus 9 over x squared plus 4x plus 10 is close to x over x squared, which is 1 over x. So I could kind of sketch a lightly dotted graph of 1 over x. It's not very accurate, but we get the idea of the behavior. And we don't take that 1 over x graph seriously when x isn't very large. So there's no asymptote here, no asymptote here. The thing doesn't even get big here and here because the denominator is pretty big. What happens is that though that out here, the graph is going to be pretty much like this one. So we know that this graph has to start off like so. And that this graph has to approach something that's very close to the x-axis. So if we extend the x-axis, we know the graph has got to get real close to the x-axis out here. And it's got to go through this point. It's got to go through this point. It's got to go through here. Well, the simplest graph I can draw that does that just kind of comes along like so. Up here, comes through here, and comes down here. Now, the way it behaves out here, it really is going to be much closer to the x-axis, probably going to dip down a little bit before it comes up, and it's going to come down. So it's probably going to have more of a shape like this, where the x-axis is right here. Okay, and that's not aligned with the x-axis up here, just get an idea, but not going to worry too much about that. It's going to do something pretty much like this. Okay. And the rest of the thing, does it have a hump down here? Does it have a hump up here? Well, to get from 9 to come up to here and down, it's going to have to hump up here someplace. It's probably going to have to do something similar over here. But where those humps are and so forth requires calculus. We can't analyze it to that point. So the big idea is, though, that the graph approaches the x-axis asymptotically, goes through the 0, and goes through the y-intercept.